So let's look at another interesting example, the so-called Humboldt law function, which is one of the common test functions for optimization. If you want, you can pause the video here and think about the global minimizers of this. What is the global minimum of this function and how many global minimizers there are? Okay, you can pause the video here, think a little bit about this. So, if you think a little bit about this, for this to be minimized, you have to set these two equal to 0. These are both quadratic polynomials, each have two roots, so you get 4 possible combinations. So there are 4 global minimizers, and the global minimum is 0. So it has multiple global minimizers. So the only thing that I need to change using the basically PyTorch is this compute loss. So I just change this. PyTorch takes the gradient for us and does the gradient descent. The other modification that I have made is that I put the logic for doing the gradient descent and keeping track of the trajectory into a function that takes the number of iterations and performs gradient descent for that many iterations. So this part is the same. The other change that I made is that I'm starting from a random initial point. So I'm using torch rand, which gives me a vector of length 2, that's this 2, of entries that are uniformly distributed on 0 to 1. And by rescaling and shifting, I get elements that are uniform in this other interval. And it's just so that we converge to different minimizers here. So every time I run this function, I start a gradient descent from a random initial point. I'm going to explain these 2 lines later. So there's a reason why we don't do this. We don't, or I don't put requires grad here. This will give you an error. But then once I have this, I'm going to run this GD function, let's say 50 times. This is the number of trajectories that I want to look at. And for each one, I'm going to store, so each run of this will give me basically trajectory, and I'm going to store it in this tensor. Okay, so this tensor is a NumPy array, 3D NumPy array. Okay, so let's run this, and it should run, and this already has the plot. You can see that, so these are the initial points, and from different initial points we converge to different global minimizers. And you can see the gradient descent can find all of them if you start from multiple initial points, sufficiently enough initial points in the middle, each of the branches converge to one of them. So this is another interesting example where gradient descent is applied to a function with multiple global minimizers. Okay, so let me explain why we did not use something like this. So if I look at this tensor, which requires grad, this is a perfectly fine PyTorch tensor, and then I'm trying to compute the loss, do the loss backward, and these all would work fine, and then I'm trying to pass this W as an optimization variable. So this is where we get an error. So you can see here that so this step raised an error, and it says it cannot optimize a non-leaf tensor. So there's this idea in PyTorch that we should only optimize leaf nodes of the computation graph. And so I've written a function that keeps or prints the state of W. So there is a property is leaf, and there's a requires grad. And so if we do this, I just need one of them for now. You can see the W is not leaf, but requires grad. So what I can do is I can define W like this, and you can see if I do this, requires grad is false, and in any tensor that has requires grad false is a leaf node by default. And then when I turn requires grad on, which you can do by calling this function, you can also set it directly as a property, I believe, but this seems to be the preferred way. So if I now do this, you can see first it's a leaf node, the requires grad is false, and then it's leaf node, and the required grad is true. This seems to do the trick. So you get a leaf node which also requires grad. So the reason why this is not a leaf node is something in PyTorch that only vectors or tensors that are created by the user and requires grad are leaf nodes. So this is not considered, W is not considered created by the user, is created by this operation 2 times this. So we can check the PyTorch documentation. So that's the part of the documentation that you can take a look. And from that documentation, that's what it says basically. So all tensors that have requires grad, which is false, will be leaf tensors by convention. So that's this. And for tensors that have requires grad, which is true, they will be leaf tensors if they were created by the user. So this one has requires grad true, and since it was not created by the user, but by this operation, it's not a leaf node. So that they are not the results of an operation, and so the grad function is not. So here, this is a result of an operation. So only leaf tensors will have their grad populated during call to backward. To get grad populated for non-leaf tensors, you can use retain grad. So you could have used this, but still the optimization would complain. So this seems to be a workaround. I'm not sure if this is the best way of doing it or if it's the correct way of doing it. But this seems to work. So we first create something which is a leaf node by not requiring grad, do the operations, and then turn the requires grad flag on.